All right, guys, let's go and get started. So what I would like to do now is, if you recall, we earlier talked about Spark's architecture. And I basically described that this is the cluster that you're using. It has the ability to run up to 4 slots on which you can run 4 simultaneous tasks. And I also showed the size of the JVM being 21.21 gigabytes and the container being 30 gigabytes. So I wanted to now show you the same thing, but using the Spark UI. So let's do that first. So we will take a quick tour of the Spark architecture by looking at the Spark UI. And then I was going to show you a little bit of maybe troubleshooting tips and how to kind of look at your JVMs that are running. And then after that, we will talk a little bit about Catalyst, the data frames and Spark SQL optimizer. And after Catalyst, we will talk about Spark stages. And then remember, we still have a few other data sets to hack on. The other data sets that we are still going to be looking at are, let me put the agenda back up. So we still need to look at English Wikipedia, revisit the clickstream data set, and then we will conclude with Spark streaming. Okay. So how do you understand the architecture of your cluster? Let's pick one. How about Samir demo? That one, the Samir demo one is the same type of cluster as what you guys are running. So the way I created this cluster is I went to create cluster, and then I can type in, for example, architecture demo. I can choose which version of Spark I want. We usually enable cutting edge versions of Spark weeks to months before they're released. So for example, 1.5 was actually released here within Databricks, I think like 3 weeks or something before 1.5 was actually released. And then we can decide, like, how many workers we want. We can choose to launch spot instances or not. You can do on demand if you don't want spot, but on demand tends to be about 10 times more expensive. So what Databricks essentially does is when you launch a cluster, let me not do a massive one. I'll do just a 2 worker cluster. You can also pass in advanced settings, by the way, like which availability zone and Spark configuration options. But what happens when you launch a cluster like this one is Databricks essentially launches a cluster in your Amazon VPC. And there we instantiate an AMI. Okay, so that takes like a couple of minutes to launch. So instead of waiting, I'm going to look at the Samir cluster, and let's do this. Let's open up the Spark UI again. Now this Spark UI is basically served out of the driver. Now remember, in our case, it just so happens that since we are running local mode clusters, in our case the driver and the executor are blended into the same JVM. But in a larger cluster, as I mentioned also earlier, in a larger cluster, the driver is separated from the executors. In which case, if you were looking at this type of cluster, the web UI, the Spark UI, would be served out of port 4040 of the Spark driver. Okay, so now remember, I'm looking at the Samir demos UI, And if you click on the Executors tab here, so I can see that this is actually a local mode cluster because the executor ID is a driver. So this executor has ran about 3,000 tasks so far for a total of about 6 minutes to run all those tasks. It's read in about 4.5 gigabytes of data. Storage memory. What does this mean? This is how much memory in the executor JVM is available for caching. This does not mean that the executor JVM is of heap size 9 gigabytes. That's not what this means. Actually, recall that I showed you on a slide that the executor JVM is actually of size 21 gigabytes JVM. But inside that 21 gigabytes JVM, between 50 to 60% of it is available for caching. Something like 25% or so is for shuffle. Another 25% or so is for like user threads. And that leaves roughly 50% or so, which is actually used for caching. And those fractions can be changed. So 21 gigabytes, 50% of that is about 9 gigs or so. So that's used for caching, but I've only used up 192 megabytes of that 9 gigabytes for caching. So this is how you kind of start interpreting what's going on in the local mode cluster. You can click on storage, and I'm going to assume that there will be one or more RDDs or data frames cached that are taking up 192 of the memory. So that one's tiny. Okay, there's a whole bunch of tiny ones. There it is. Right, so that makes sense. Okay. But this is just a small cluster. How about a bigger cluster? How about the 8-worker cluster at the top? How would that look? So let's open this one up and go to the Executors tab. So one thing you might notice is, though, even though it says 8 workers here, it looks like there's 9 executors here. This is a bit misleading because there are actually only 8 executors. Executor ID 0 all the way to 7. And actually the driver runs some of the same Scala classes that run and get instantiated in the executor also get instantiated in the driver. So currently a register is almost as if it's an executor. Hopefully that will be changed at some future version of Spark so the driver is kind of separate. And then it won't be as misleading because this should really be 8. So here in a larger cluster, though, I can see the storage memory is actually caching different partitions of the data frame or the RDD across different executors, and none of them are in the driver. That's how it's supposed to be. You cache on the worker machines or the executor JVMs. This cluster has been used a lot more. Right? It has run many more tasks. You can click on thread dump. If you do that, you essentially, it's like you get a snapshot of, at the point I clicked about 4 seconds ago, what the thread dump looked like. And remember I said that in the clusters, there's some internal threads for shuffle, and like there's a thread for broadcast, there's then a thread waiting state. You'd find worker IO threads here as well for the actual work that you might potentially do. You can also click on one of these and get the more of the call stack. So the reason I like this is, you know, to really profile your application, you'd have to connect some Java metric like so that collects JMX metrics like JConsole or something like that to your JVM. But this is like a cheap and dirty way to just quickly see what's going on in the actual runtime. And if you can profile your Spark application by capturing the thread dump multiple times in sequence and then looking for things like hotspots or parts of expensive code in your application. You can also see the standard out and standard error log of each executor. Okay, so I showed you those two tabs. Let's now go back here, and if you expand this, now this is a Spark standalone cluster. In a Spark standalone cluster, you have worker JVMs and one master JVM. So here, let me show you kind of how this works. If I click on master, this shows me all of the worker IDs and all the different machines they're running on. Each one of these worker IDs is a JVM. It's a small one. I think it's like maybe a half a gig or 1 gig goes to the worker JVM. So the way to really think about this is that, let me actually go to this slide here. So the way to think about it is here in the container, there is actually some other stuff here as well. So hang on, let me look at some of my shortcuts here. Okay. All right, so in the executor JVM, there are other things. So I'll draw the worker JVM. Oops, I should do it like this. So imagine that is like the worker JVM, and that worker JVM is kind of what starts the executor JVM and makes it highly available. But you don't have this worker JVM in standalone mode. So in standalone mode, you just have this. You get the little worker JVM when you're actually running Spark standalone. So for example, I'll show you that. If I come back here, let's see, to clusters, and if I look at one of the random student clusters, now it looks like there's a master here, but if I actually open this, it'll just open up the Spark driver UI. The same thing will open up if I go here or if I go there. So in local mode, basically, there's just one JVM. All right, but if I go to a real cluster that has many machines, and then if I go to the master UI, this is now a Spark master JVM. And what the master does is it basically, this is kind of a resource manager. The Spark master and the Spark worker JVMs, they make a resource manager platform to manage your individual Spark applications. A specific Spark application is, remember, always made of a driver JVM and multiple executor JVMs, right? And that is your Spark cluster. So the Spark cluster that I had drawn there is managed by essentially the Spark master and these workers. If you're using Yarn, and I believe 60% of you, I think, said you were planning on it, then you're not going to have in Yarn a Spark master or a worker JVM. With Yarn, the role of the Spark master is essentially played by the Yarn resource manager, the Yarn, the master for Yarn. And the worker JVMs, these are like the node managers, right? You can think of that as an analogy. But in this class, we are more focused on actually writing code and using Spark. So the resource manager layer is kind of like just this abstraction on top of our cluster. But I figured maybe that would be interesting to point out some of those things here. You can also go to like one of these worker JVMs, and you can see that this worker JVM has launched executor ID 0 So these worker JVMs they launch their executor, then they make their executors highly available as well. So technically, you can imagine that there is like some container that has a Spark worker and an executor together in that container. Okay, so that's a little bit about architecture. The other thing I wanted to point out was I thought it'd be maybe cool to do like a quick troubleshooting demo. So let's close these things out. If I go back to users and admin, I have a few demos I'd made here that, time permitting, I was going to do. So I'll connect to, I guess, this one. And I'm going to switch over to Python and import subprocess, and I'm going to run this command. So once again, we're going to conclude with showing you the actual JVMs that are running. So this is just printing out like memory information on the EC2 physical machine. But let's skip down to this one. So this is showing that on the executor JVM, on this Samir demo cluster's executor JVM, remember this is a local mode cluster. So basically there's only one executor / driver. In here, in that type of cluster, so what I'm doing is I'm running the JPS command in the container that has this JVM. Right? So I'm basically running the JPS command in this container. And what do I see when I do that? Well, that's the command, JPS, but I see a driver daemon. And this is basically our executor JVM. So if I do this and print it out more verbosely, I can see all this information about the driver JVM. Like, for example, it can grow to a max heap size of 21 gigs, basically, 21 gigs, but it starts out at 21 gigs as well. So this is how I was able to figure out that each one of your JVMs is a 21 gigabyte JVM. So remember, 21 gigabyte JVM, and this is now showing that this Java process is indeed starting and allowed to grow up to being a 21 gigabyte JVM. So now this JVM, though, that is a 21 gigabyte JVM, allows up to 9 gigabytes of caching in memory, about 50% of it. All right, so basically, English Wikipedia uncompressed was 50 to 60 gigs. This could be a challenge. So let's see how, we'll come back to this topic and see how we can kind of make this small cluster still crunch English Wikipedia. There's a bunch of other JVM options that I can see here. Okay, what's this next command? Ooh, this is a little challenge question. So I do this print. Well, in a local mode cluster, there's only one JVM, so it's not interesting. Let me connect to a larger cluster. So what were the other clusters? Let's connect to one of like the more, I wonder if that architecture cluster launched. Yeah, remember this architecture demo cluster that has 2 executors basically, so 2 worker JVMs and therefore 2 executor JVMs. This is a standalone mode cluster. It has basically a Spark driver and 2 executor JVMs. And those 3 are managed by a Spark master and 2 worker JVMs. Okay, so what are we doing here? What's going on? I'm going to connect to the architecture demo cluster and show you like a little troubleshooting tip that you might find useful. Let me make this a little smaller. There we go. It's connected. And this cell shows output, but remember, this is from the earlier cluster. So now I'm going to run this. And the question is, I want to find out where the print line actually printed? Which JVM's standard out did this print in? So I'm going to take a quick poll here. You have two choices. Choice A is the driver JVM and for this cluster. So let's go and open this up right here. Okay, so here are the executors. This specific architecture demo cluster has two executors, 0 and 1, and I can look at the standard out for the executor JVMs there. Or that print line might have printed in the driver logs as well. All right? So how many people here think that when you do this, it would print in, remember, option A will be one of the two executors. Option B will be the driver JVM. So this will give me a sense of just how much you guys know about architecture and perhaps how much I would want to cover in the rest of this class. So let's do a quick poll. How many people think this printed and I should go and check one of the two executor JVMs? Okay, a handful of people, maybe 6, 7. How many people think that maybe this printed not in the executor JVMs, but maybe the driver JVM? 90%, okay. I'm surprised. You guys are correct. Most people don't get that, actually. That is correct. Let's go down here to the standard out log, and there it is, 5. That printed in the driver logs standard output. Therefore, my takeaway here is that when I do math in a cell, that is running in the driver JVM. The driver JVM is simply a Scala REPL that has been slightly modified with some additional lines of code to not just be a Scala REPL, but to also instantiate a Spark context and a Spark SQL context to give you some additional functionality. Okay. Moving on, I make a Scala array. Remember, Scala code runs in the driver JVM. I'm not doing anything with Spark right now. I'm just declaring a value called word list with 5 strings. And then I'm taking that word list array and passing it in to the Spark context parallelize method and saying, give me an RDD with 1 partition. Call that the words RDD. We should have these words in it. Okay, then I'm going to call count. Five. That is correct. 1, 2, 3, 4, 5. That is correct. Now what I want to do is, on the words RDD, call the map transformation, and then for each one of those items, I want to print it. Now, technically, this won't print anything, and I'll just cut to the chase and tell you that the reason this will not print anything is because the map is lazy, and you have to actually call an action like this before something will print. So now it's actually executed. This was just building a DAG, a directed acyclical graph, which got executed when I called an action. So now, for this one, where would I go and check where this might have printed? Notice that on the words RDD, which lives out in the executors, basically, I'm calling map, and then I'm printing during the map call. Map calls run in executor JVMs, so that is where I'm going to go check. If I go to the driver logs, it won't be there. I want to try to go to the executor JVMs, and let me open up both standard outs, because I don't know really where exactly it might have printed. Actually, I can check. See how there's 0 tasks that have run? Remember, our words RDD was 1 partition. If I click executors, I can see, you know what, I called count twice, so I don't know where it actually ran. Okay, let me go look at both of them. Here is one of the standard outs. So I'm looking for some words. Doesn't look like it's down there. Let's see if it's in the next one. There it is. Now, this is like pretty trivial troubleshooting, but sometimes being able to just do a print line will get you pretty far in your own troubleshootings. Okay, so we learned how to print stuff in the driver's standard out or the executor standard out. I thought this would be a cool thing to show you as well. We're getting the Spark configuration, all of it, and then just running some Scala code to pretty print it. And now you can see how Databricks essentially launches our standard clusters for students. Perhaps a good way for you yourself to configure your clusters to launch out of the box if you're doing like an on-prem deployment. Now, a lot of the Spark configuration can also be viewed by going to the clusters environment tab. So you can see a lot of the same settings will show up here, maybe in a nicer to view place, nicer to read. Okay. So that concludes the architecture and troubleshooting demo. So you are always working in a distributed environment when you're working with distributed systems like Spark. So knowing the Spark API, whether you're using data frames or RDDs, will only get you so far. You also should embrace the fact that you're running in a distributed environment and know the challenges and pitfalls that you can potentially run into by understanding the architecture and knowing the new techniques for how to troubleshoot these type of applications. Okay. Next, I was going to mention that, remember when before we went to lunch, we ran this lab, the Clickstream lab, and if you recall, at the end of the Clickstream lab, we ran a couple of explain statements. So let me go all the way down, right here. Remember these two? So this was running explain to just look at the physical plan first, and then explain true shows a bunch of stuff. What does it show? Parsed logical plan, analyzed logical plan, optimized logical plan, and then finally the physical plan, and code generation is set to true. What does all of that mean? Well, I thought I would unravel that mystery over the next few minutes. So Catalyst is an optimizer for data frames and Spark SQL. Catalyst is not used when you're working with the RDD API in Spark, the traditional API from back in Spark 0.0 days. But Catalyst is newer. It's one of the fastest moving projects. I believe in the past year, the amount of code for Spark SQL has tripled. How does this work? Well, you take your data frame or your SQL statement, and you make an unresolved logical plan, and then you feed it a catalog, which is basically the types and column names from the external data source. You get a logical plan. From the logical plan, you do some optimizations, logical optimizations. And then you do physical planning. And then you generate some potential choices for physical plans. And then based on cost, you don't choose, Catalyst chooses a physical plan for you. So this is essentially what we were seeing when we ran those explain statements. And code generation can sometimes be turned on to compile parts of the query down to Java bytecode. This is what makes Catalyst so fast. So the whole point here is we need to take our data frame operations and convert it to the correct physical plan so we can actually run the code. And data frames in SQL share the same optimization under the hood. And I wanted to talk just a little bit about some of the logical optimizations and the physical plan optimizations as well. So at a high level, there are two kinds of optimizations, these two. So first, Catalyst applies logical optimizations such as predicate pushdown. This is where the filter gets pushed down to the data source. This is pretty cool because if you're reading from data sources like JDBC or Cassandra, instead of doing a full intake of the data from JDBC, a full read of that table from Cassandra, instead of that, you're going to push your filter all the way down to the data source and let the relational database or the NoSQL database do the filtering for you and then just give you back some subset of its data. Much faster than doing a full read and then filtering in Spark's memory, which you would have to do if you were reading from S3 or HDFS. Those two file systems, or S3 is more of an object storage system, but HDFS and S3 don't support predicate pushdown. So you have to do a full intake read and then do a dot filter in Spark. Now there's also Parquet. This data format lets you skip entire blocks and parts of files. So even if you're in HDFS, as long as the type of the file is Parquet, you can still do this type of selective read as opposed to full file reading. Okay, and then the other interesting thing is physical optimizations. So here things are done, for example, choose between broadcast join or a shuffle join. By default, if you need to join two data frames, and if one of them is, I believe, less than 10 megabytes, then Spark will broadcast that smaller data frame from the driver to all the executors. And now every executor has a copy of that smaller data frame in memory, and it just does a local join. However, if both data frames are quite large, then it will have to do the join in the executors themselves, partition by partition. Okay, so just wanted to give you a high-level overview of that, and also then bring it home with this diagram. Here we have a logical plan. We are reading a users table from some JSON and an events file from some JSON, joining them, and then doing a filter. Now, if you use RDDs, then this is exactly how it would have happened. You would read an RDD, read a different RDD, join them, and then do the filter. But the power of using data frames in Spark SQL is the Catalyst optimizer, which would, in this case, convert the logical plan to a physical plan. And what it has done here is moved the filter down to occur before the join, so that when you read the users table from the same JSON, you now do a filter first so that you are doing a join on less data. And, well, JSON's an okay data source, but I like Parquet more because Parquet lets you do cool things like column pruning and predicate pushdown, where you can tell Parquet, well, I only need 4 columns out of the 50 columns I have in my Parquet file. And since I only need 4 columns, don't read all 50 of the columns. Only read 4 of them. Versus here with JSON or CSV, for example, I would have to read all 50 columns or all 50 fields in the JSON. Okay, so some tricks here for how Catalyst works. And if you want to learn more about it, I highly recommend checking out this Databricks blog by doing a Google search for this title. If you're interested in Parquet, I have a couple of slides here. The way Parquet works is, traditional databases store data in a row layout. So if this is your logical table representation, like this is how you think about the table in your brain, in like a human brain, you think of columns and rows. Well, the way most databases store this is in a row-oriented way. So A1, then B1, then C1. So the whole row. And then A2, B2, and C2. That's the row layout. When you do things like this, though, you usually have to read this data. You usually have to read the entire row and deserialize it. And if you only needed one of these columns, you're paying the cost of reading the serialized data off of disk of all three columns, the CPU cost of deserializing all three columns, and finally getting back the one column you wanted. There's a better way. The way column-oriented data stores work, or data formats, column-oriented data formats like Parquet, for example, work, is they take the entire column and store that together in a file. The next column gets stored together in a file, and so on. So now, if you only needed the A column, you would, in this case, only need to read the files for the A column. So technically, it doesn't like take the entire column, because you might have a billion items, a billion rows. So it basically makes boundaries. Let's imagine a boundary is at 10,000 rows. So at 10,000 rows, it makes a boundary here. It takes the first 10,000 values for column A, folds them into a file. Then it goes down to the next 10,000 columns for column A, folds those into a file. So how does that look like? This diagram shows row groups. So remember I was talking about the first 10,000 rows, then the next 10,000 rows? Imagine that maybe the first 10,000 rows are a row group. In that row group, we are going to store all the columns in the first 10,000 rows. So that row group, the first row group is there, row group 0. The next 10,000 is row group 1. Inside row group 0, I have column A being stored, then column B being stored. So if I need to read column A, I can do a seek and a continuous scan to read out all of column A without touching column B. At the end of a Parquet file is a footer. This footer describes basically where all these different data boundaries start and end. When you read a Parquet file from Spark, you might be confused if you read a Parquet file and then go to the Spark UI to look at your job, like which job launched. You'll be confused because when you read a Parquet file from Spark, what Spark will do is first shoot off a preliminary job, a small one that has nothing to do with your data analysis. It's only being shot off because you're reading a Parquet file. And that small job will essentially read the footer of the Parquet file to understand the structure of your Parquet file and directory. After that first job runs and understands your Parquet directory, this is like inferring the schema of Parquet. Then the next job is actually going to be your real workload. Now, one other thing is if you go to Spark Docs and then go to the programming guide and search for Parquet. Actually, no, not that. We want to go to the data frames in SQL, Parquet files. So here's where you can learn more about Parquet and how Spark works with that. how it does partition discovery, and the setting I'm looking for is cache metadata, which is set to true by default. Turns on caching of Parquet schema metadata. Can speed up querying of static data. What does this mean? What this means is if you start a new Spark cluster, point it to a Parquet file, read that Parquet file, what is going to happen is this initial job will run to read the footer from Parquet, and then that footer information will get cached in your cluster. From that point onward, if you keep trying to read that Parquet file, it doesn't have to go read that footer anymore. It will just run your actual job because it already knows, it has cached this metadata from the Parquet footer in memory. Now there's a repercussion here. If it did the cache and then you appended to that Parquet file, that new appended data will not show up in future jobs because your cached metadata does not know about it because you cached this metadata before you appended the data. Right? So the way you fix this is if you either refresh your table like this, meaning go back to my underlying data source and see if there's a new footer that tells you about new files that were appended to my Parquet directory. That will fix it. Or if your Parquet data is always changing because you're appending every few seconds and you always want to read the newest Parquet file data, then set this to false so that every time you read from Parquet, you're forced to shoot off that initial preliminary job to read the footer every single time so that you can get all the fresh data every single time. All right? So that is Parquet, and I would highly encourage you to, if you're going to work with JSON or CSV type of data, usually the very first thing you want to do is read that data into Spark and save it right back down as Parquet. And then work on the Parquet version of your data. Don't work on the CSV or JSON version. This will be a massive speed improvement because of the things I described. Okay. So let's get some things closed up and get ready for the next thing. Okay. I was going to talk a bit about stages next, and I was going to do this through a demo as well. And then after this, we'll start doing some real coding by analyzing the English Wikipedia. But to analyze the English Wikipedia, I encourage you to use RDDs, especially when you're working with like the unstructured text in the article of the English Wikipedia. So when you're working with unstructured text like that using the RDD API, it can help to understand something called stages in Spark. And when you use, actually, let's go and jump right into the demo first. So to explain stages, what I was going to do is take a small detour from Wikipedia and talk to you about another one of my favorite projects, which is the Project Gutenberg, which is a collection of books that are in digital form essentially, and these books have basically their copyright has expired, so now they're in the public domain. Books like Tom Sawyer, and many other books. I think it might be in the thousands, or here we go, at least 50,000, but I thought it was even more than that. So, I mean, it could be cool to actually also download all of Project Gutenberg and do some analysis on it like we're doing with Wikipedia today. So to kind of get you started on that path and perhaps do interesting joins between Project Gutenberg and Wikipedia, I thought maybe I could show you the Tom Sawyer book and show you that it's basically just a text file. The first line is actually empty, and then we have this line. This is the third line. Fourth line is empty. This is the fifth line. This is just some licensing information or something it looks like. And then we get to like a table of contents. eventually we'll get to like the actual chapter 1. Illustrations. Preface. Here we go, chapter 1. Okay. So this is Tom Sawyer. Now, this book, notice, is 412 kilobytes. It's half a megabyte. It's not large, but it's sufficient to demonstrate the things I'm going to demonstrate right now. So half a megabyte file, 412 kilobytes. So if I go to Workspace, and once again, what I'm about to do next is, we already did that one. It's going to be this one. So if you go into your home folder, if you want to follow along, you're welcome to. Or, like I said, this is all on YouTube. You might just want to sit back and try to get a sense of what I'm doing, because you can review the video later. Or you can go to this notebook and run the same exact stuff I'm about to run. The main thing I hope you get out of the next 10 or 15 minutes is you understand what this internal architecture thing inside of Spark is called stages. It's quite powerful to understand what this does. It basically will help you debug, troubleshoot, and performance optimize your code when you're working with the RDD API. When you're working with data frames are actually translated down to the RDD API, and when data frames get translated down to the RDD API, there are only 3 things in the RDD API that data frames leverages: the map partitions transformation, zip partitions transformation, and it can call a shuffle. So all of data frames decomposes down to one of these 3 operations, one of these 2 transformations or a shuffle. But the RDD transformations have a lot more than that. Like, I'm sure you guys have already been playing around with this, but if you go to like Spark Docs again and go to the programming guide and then the transformations, you can see there's quite a few transformations, right? Map partitions is used by data frames, but not these other ones are not. But if you work with the RDD API, you can get all of these. And at Databricks, we in our 3-day class, we have a slide deck where we actually try to organize all these transformations and actions in a way that would perhaps make it easier for people to think about them. I'm going to put that slide up for just a second so it goes on YouTube for this talk. And then I'm going to just jump right into explaining stages. So let me pull this up right here. So here's one way we decided to organize the different transformations and actions. You can see there's white belt and blue belt ones. The medium blue belt ones basically means like use with caution. Make sure you understand what's going on there, because there's some performance implications if you don't use it correctly. But you can see that we basically classified the transformations under, or actions as well, under columns like general, math, statistical, set theory, relational, and data structure I/O. And then in addition to these transformations and actions that work on any type of data, there are other transformations and actions that work only on pair RDD data types, pair RDDs. These things basically, this means that your RDD has key value pairs. This means your RDD might have images, words, non-key value stuff. Perhaps, but when you have key value items in your RDD, then you can do joins on the key. You can group by the key. You can get just the keys or the values. Right, so I just figured this might be an interesting way for you to look at this. Okay, so now let me go back to my demo. And I will actually go to the copy of it that is in my own folder. stages. All right, and I will connect to a cluster, and I will open up the cluster's UI like I always like to do when I'm working with Spark, so I can see what's going on. Actually, let me do yeah, I guess that's fine. Okay, so we already actually covered this first stuff in the earlier lab. You can notice that on an RDD, you can run partitions.length to understand how many partitions are in that RDD. When you make a base RDD, the number of partitions is decided by your input data source. So, okay, let's move on to understanding stages. So here I'm just printing out the Spark context, checking which version of Spark I'm running. Databricks Shell is the app I'm running. SC default parallelism is set to 4. So if you parallelize something, like if you take an array and you send that array to the Spark sc.parallelize method, you'll get an RDD back with 4 partitions. Okay, so I want to actually read my Tom Sawyer data set. And I actually have this data in a different location than this notebook is looking for. Actually, let me try running it. Maybe it's also available here. Yeah, it's not there. I do know where it is, though. So I'm going to load that up really quick. Give me just a second while I do this. So then we're going to basically, I'm going to explain to you what the whole stages thing means, but I'll also refer you to typing in data bricks, blog, visual. I think it's just under visual. No, maybe Spark UI. Yeah, so see this blog right here is actually by Andrew Orr, who's our TA today. So he's in the back, and he wrote this blog. He mainly is one of the engineers who worked on this new feature that came in, I believe, Spark 1.4 that lets you understand what's happening in your Spark application. So that's what we're going to do. We're going to try to understand what's going to happen in a really simple Spark application. And if you didn't quite follow what I'm going to explain in the next 10 or so minutes, then I would refer you to this blog post, which will kind of explain what I'm about to do right now. Okay. So first, I need to find my Tom Sawyer file. Notice that in between cells, there's a plus button that I can hit to open a new cell. And then I want to list everything under the read-only folder here. And there should be a Tom Sawyer folder, which should have in it a 412 kilobyte text file of the Tom Sawyer ebook. There it is. That is the same as this book. I just moved it in there earlier for this demo. So now I'm going to load that up. Okay, well, I already did that command. Here we go. So let me make this a little bigger so I can see from back here. Notice what I'm doing here is I'm saying when I read this, after this, give me an RDD with 2 partitions, and then collect the data back at the driver, in this case, to the notebook. Oh, oops. Okay. Here's a best practice. If you want to understand what's going on in Spark, do what I'm about to do for the next 10 minutes for the first few days that you continue like hacking Wikipedia. Okay, so as soon as I run a command, I like to go to the UI, hit jobs to refresh, and I like to go to the last job. This is the last job. So notice here, it's the show how, it's this cell. This is the job. What I always like to do is come and look at the job and see if I can figure out what's going on. So I'm going to click on this. This specific job had one stage, and the stage read 412 kilobytes of data. Well, so far so good. 412 kilobytes. If I click on this, I will see that there are two tasks, two threads that launched in this stage, each of which read half the file. 7,700 lines and 4,700 lines and 4,400 lines. Each task read half of the file. Interesting. I can also do this. If I click Event Timeline, this shows me those two tasks. See these two tasks down here? These two tasks ran in the same executor ID. This was a local mode cluster, so it was just one JVM. And in that JVM, I ran two tasks. The green here is the actual compute time. In this case, computing means reading. So I was just reading. And then the purple is result serialization time. The red here is task deserialization time. Okay. Let me make that smaller again. And let's look at the DAG visualization this time. So what does this mean? This is just showing that this stage reads a text file, and then you get a map partitions RDD after that. Let's do a couple more things and just kind of see what happens when we run different commands. So hopefully I still have this. Yeah. So now I am just doing a collect. When I do that, a collect is being sent to this value ebook. What type of data is that? Well, this is not going to work because collect does not give me back an RDD. Instead, collect gives me an array. So perhaps I could do something like this and then assign the data file to an RDD, like ebook RDD, and then I could do a count on it. Oops. (9,200) rows or lines. 9,000. This is not structured data. This is unstructured data that is being read with sc.txt file, which reads one line at a time, and it has read 9,200 lines. This plus 4, 4, 6, 7. I can't make that out, but maybe I just type out it something. (9206). 9206. How many partitions are in my RDD2? Right, these are all tricks you can do when you're troubleshooting things on your own, when you're trying to figure out what's going on in your Spark application. Maybe I want to print out the different thing, how many items are in each partition. Now, this is important because now I know that I don't have a lopsided RDD, where I might have, for example, 20,000 partitions, but maybe 90% of my data is in just one partition. That would be computationally a bad way to run, basically. Right? You want to have roughly equal amount of items in each partition. So this is what this code is just checking for, how many items in each partition. So here, what are we doing here? We are, oops, I need to get my, So we'll conclude by just building out some stage diagram. So I'm going to take this, and I'm going to start doing some transformations and actions. Let's go back down. Right here. Okay. So let me replace this with the correct path. And then we're going to run these transformations that you see here. And then we're just going to go and look at the stages UI to try to understand how our Spark application is creating stages. Okay, so I think that should get us there. One more. And then we'll stop like around here. So this is the stuff that will help you work on the 50 to 60 gigabytes of Wikipedia in an efficient way, because we're going to take a short break after this and then hack on that data set. Okay, that's good. That's all you need to hear, I think. So see if you can okay. What did this do? That's not important. This is what I care about, actually. Actually, no, let's go ahead and do this. Right there. Okay. So I'm reading my file, sc.txt file. I'm saying, give me back an RDD with 2 partitions. Run on that a flat map. What is this doing? This is taking every line in my RDD and splitting it on white space and then giving me back a bunch of words. Now I have a bag of words. I do a collect on it to bring those words back to the driver from the 2 different partitions. So now that I ran this, remember best practices tells me that I should come back here and look at what my stage diagram looks like now. There's only one stage, there's no shuffle. I read the data, these black dots are RDDs, and I do a flat map, which gives me a map partitions RDD, and then I do a collect on it. All right, so I read some data, then I do a flat map, I read some data, then I do a flat map. This is all within the same stage. What does that mean, same stage? Well, we're pipelining. What we're doing is, you might look at this from a logical perspective. You might think, well, I'm going to launch some threads to read the file. After those files are read, I'll launch some threads to do this operation. When this operation is done, this flat map transformation, then I'll launch some more threads to do a collect. That's reasonable to think, but that's not what happens. What instead happens is something called pipelining. And how do we understand what pipelining means? We go all the way down. Notice that this entire job, the job here that we just ran, this one, right? Show how these 2 operations in the UI. Oops, I meant to do it. Organize it by this. There we go. It only needed 2 tasks. Only 2 tasks to run this. So we basically are, what we're doing is we've pipelined. We launched one task to read half the file, and then we did this operation. We launched another task to read the other half of the file, and we did this operation, all of it. Let's just do something a little bit more complicated. After the flat map, let's do another map. And let's look at the output here. Now I'm making key value pairs. I'm building up to a word count, but I'm deconstructing that word count for you slowly. I do a map. I take the entire bag of words, and for every word, I make a key value pair out of it, the word, comma, 1. Again, let's go look at the visualization now. I mean, before I even do that, notice still only 2 tasks like before. Even though I did a whole new transformation here, I still have only 2 tasks like before. However, my diagram will now account for the fact that after the flat map, those same 2 tasks that were instantiated are not let go until they also do a map. So I'm pipelining the read and the flat map and the map in the long-running task, the 2 tasks. Next, to complete the word count, I need to do a reduce by key so that I can bring together all of the keys that are similar. Like I had the word nose 5 times. So I just tacked on after the map a reduce by key basically. Again, let's go back here, jobs. Now notice there are 4 tasks. Let's look at this. Ooh, something else happened. Reduce by key is a wide operation. That means that it's going to cause the shuffle to take place, an expensive all-to-all network shuffle. And that is what has happened here. And we got a new RDD that basically materialized after the shuffle. This new RDD will inherit the number of partitions from the earlier RDD, unless you override that by, when you call this wide operation, you can do a comma X to say that after the shuffle, you actually want to control the number of partitions and not inherit the number of partitions from the earlier RDD before the shuffle. Okay, so I think I have an example here. You can do something like this, like comma 4, to say that after the shuffle, I want the next RDD to have 4 partitions. So now, if I come here, go to jobs, notice that instead of 4 tasks, there are 6. Because the first RDD in stage 1 had 2 partitions. After the shuffle, the next RDD, the second RDD, had 4 partitions. So I need, in stage 1, 2 tasks, stage 2, 4 tasks to crunch through an RDD with 4 partitions. So this diagram will look the same, basically. But what I'll notice here is that now the second stage, this stage, is working an RDD with 4 partitions, because I passed in comma 4. This is how you can control the size of the partitions in your RDD. So this is a pretty important setting if you want to learn how to really scale. Now notice this, right? Like in your cluster, you guys have 4 cores in your machine, right? Remember this diagram right here? You have 4 slots which can run up to 4 tasks simultaneously. This means that if you make an RDD with just 1 partition, you're only going to use 1 of your 4 potential slots. You can make an RDD with 8 partitions if you want, but then it will first launch 4 tasks to read the first 4 partitions, and then launch 4 more tasks to read the next 4 partitions in the RDD. Right, so this is how you link your developer work to the architecture of Spark. Okay, I think that concludes basically the demo I wanted to do, but there is maybe 1 or 2 things I wanted to tell you. I wanted to tell you that in the world of data frames, now we were talking about RDDs. Everything in that demo was RDDs, not data frames. In RDDs world, when I go look at that DAG visualization, it's pretty easy to interpret after you understand what I just mentioned. But in the world of data frames, if you remember, like it just throws up like a whole bunch of stuff that Catalyst creates. With data frames, you don't have low-level control. It's a much higher API. So whatever it translates down to might be kind of like black magic for you. So in data frames, what happens right now is after a shuffle, there's this setting which defaults to 200 in Spark, which means when you're using data frames, every time a shuffle happens, the next data frame will have 200 partitions. It's a statically set number. You can change it like this if you want. The key would be this. The value would be not 300, but not 200, but 300 maybe. That means if you set it to 300, every time your application does shuffles between two data frames, the second data frame will have 300 partitions if that's what you set this to. Now, this is kind of weird because if you're working on a 2 megabyte RDD or a 2 megabyte data source, you probably don't need 200 partitions. Ideally, a partition, whether it's an RDD or a data frame, ideally a partition will have somewhere between 50 megabytes to maybe 200 megabytes. So anyway, I wanted to mention that in Spark 1.6, there's a new feature coming called Adaptive Shuffle, which will basically adapt dynamically how many partitions should be in the data frame after the shuffle. So that is coming. And I also thought maybe I should leave this slide up. This is just comparing RDDs to data frames. Data frames give you all these features. I won't read through this, but I'll let you skim through it. RDDs give you these features. Data frames or Spark SQL gives you these features. In general, always try to use data frames in SQL if you can. If you need to operate on unstructured data, like in the case of Wikipedia, which we're about to do after, we'll take a short break right now. After that break, we're going to hack Wikipedia. When we do that, instead of doing just RDDs, one trick you can do is when you read Wikipedia, the 60 gigabyte corpus, you basically get like 20 columns. One of those columns is called named article. In it is like all the article. It's like unstructured text. To process the unstructured text, you can still use data frames in SQL by writing a UDF, a user-defined function that you call through the data frame that then maybe goes through all that article text and derives something out of it. So then this is a way to actually work with unstructured data, even if you're staying within the data frames API. Okay, so before I get to exploring Wikipedia, that was a long theory section. Let's take a break for, let's see, it's 2:20. Let's take like a 15-minute break. All right, and then if we can, I'd like to talk about this and then do GraphX and then take one more break before we do Spark streaming, because I want to make sure we connect to the live stream of edits. So please come back. It's 2:20 at exactly about 2:35. At 2:35, I'm going to start talking about the English Wikipedia. Okay, let's go and get started. Before we tackle the 60 gigabyte corpus of English Wikipedia, I thought I would show you one more of the questions from the pre-class survey. Which of the following best describes your role at your company? So you guys are basically overwhelmingly developers and software engineers. 95% of you identified as that. You'll notice that you were able to select multiple answers. About 30% of you were also identifying as data scientists or as machine learning people, and 21% or so administrator or DevOps. Okay, so this is what the English Wikipedia looks like from a schema perspective. There is a title column, ID for the article, article ID, revision ID, revision timestamp, who did the last revision, that guy's ID, and the actual text. Right? You can see all of that here as well. So, okay, let's just get to it. So, most of the rest of the day is just going to be hands-on. That was a lot of theory after lunch, but that's mostly out of the way. There will be a little bit of theory to set up for GraphX, to introduce you to how graph processing works. But it's pretty interesting because there's a lot of visualizations. But like I said, most of the rest of the day is going to be actually hacking some Wikipedia data sets. So this is the mother load of Wikipedia right now, the snapshot of English Wikipedia from, I believe, 2 weeks ago. I loaded this on here just a couple of days ago, actually. The latest version that you can currently download is this version. It's a very fresh version of Wikipedia. It's right here. Now, this is a relatively short lab. The idea here is to, I could spend all day probably doing nothing but hacking this data set. I just wanted to kind of get you into this data set, to introduce it to you, make you comfortable with it, show you how to analyze it using data frames and RDDs, and then let's move into graph processing on the clickstream data set and then do the Spark streaming with live Wikipedia edits, right? That way I can cover all of these things as opposed to spending a lot of time on this data set. Okay, what are you going to do? What percentage of Wikipedia articles were edited in the past month? A whole bunch of interesting stuff. Okay. So I'll let you skim through some of those questions so you know what's coming. All right. So the only technical accomplishment right now is quite significant. What I'm going to do here is something a little bit different. Instead of attaching this notebook to the smaller 30 gigabyte, local clusters that you guys are on, the 30 gigabyte container, but technically a 21 gigabyte JVM that you're on, instead of that, which this notebook works on your clusters. I tested it last night. It will work fine, but the problem is to read the entire 60 or so gigabyte corpus will take about 7 to 8 minutes. And I figured, instead of doing it and waiting for that, why don't I do it on a larger cluster? So I have here a cluster with 16 executors. And each executor has 4 cores. So 16 times 4 means I can do 64 threads in parallel. 64 tasks can be run in parallel across my 16 executors. So, what you can get out of this is perhaps you can now see how fast it might be if you did this in a real cluster. Okay. So we're just going to load the data first. Actually, before we even do that, let's just look at what the data looks like. You'll notice I've converted the data to Parquet already. How did I do that? Well, let's wait for that to finish. There we go. So all this data is Parquet. There's more than 1,000 files. So in Databricks, we give you some helper notebooks. If you go here and then go to Databricks Guide, there's a bunch of, this is the manual for using Databricks and Spark. There's a lot of cool things described here, accessing data, visualizations. What we want to see right now is under Sample Applications Wikipedia. If you run this first notebook, they're in Python or Scala, you basically just have to run this cell and put in your Amazon credentials and then run the notebook. If you do that, then this is going to go to the internet, download Wikipedia, put it in your S3 bucket. And then you can run this one to convert it from the XML that you get it in into Parquet. All right, so how do you run this? You have to clone this notebook because Databricks Guide is all locked. These are all static notebooks, just like my labs folder is locked. You cannot edit them, but you can clone it out into your own folder. You hit clone, move it into your own folder, I'll move it into my labs folder. And if I hit clone there, and then if I go to, here, users, there's the notebook that I'm just going to delete for now. That's the copy of the notebook that I cloned. Anyway, with that being said, let's do this. So it's connected to the cluster. Let's make that a little bigger. I already showed you the Parquet files. So basically, for the next month, you don't have to worry about trying to download this corpus. You can just access it off of the Databricks S3. There's more than 1,000 Parquet files, and actually it compresses down to like 10 gigabytes here. Let's read the Parquet data and then lazily cache it. So that command didn't really read it. It just comes back in a second. Also, the print schema command does not read it, not the full data. It's going to show us the schema of Parquet. This is the same thing I just showed you on the slide. Right? Let's look at, in the data frame, do show to just pull out the first 2 articles and then look at them in a tables perspective. So I might make this a little smaller so you can kind of see it. All right, I guess that's not going to format very well. So one thing I can do is I can do display on here as well. However, if I do display like that, it would start reading everything. So I'll just do, you can do like a limit on here basically, but it seems to have already, since I paused it or canceled it, it did read some of them in already. Title ID, revision timestamp. Let's start answering some questions. Well, actually, first let's count how many articles there are. You know, English Wikipedia is under 5 million articles. It's like 4.999 right now. I think I didn't prune my data enough and I got some extra stuff like talk pages or something. I was trying to be diligent, but I'm not sure. If you figure out what the other stuff is, drop me a line on LinkedIn. Okay. So remember, there's like roughly 5.8 million articles here. Oh, since I did the count, it must have loaded this into memory. Because remember I cached it earlier? Let me just double check. Storage. Wow, more than 1,000 partitions, 100% cached. In memory, it's 31 gigs. How much is each partition size, though? It's on 16 executors, actually, not 17. Host, memory usage. The first one is the driver. It just shows up in here for some reason. Okay, I got like 2 gigabytes in memory on each one of my 16 machines. I have pretty good parallelism here. 64 threads can run in parallel to analyze this data, and there's 2 gigabytes in memory. I should get some good speeds. I already checked it's all in memory. Count in memory might be fast. And remember, when I do this count this time, it's literally going through all of Wikipedia. Now, let's see how long it takes. I've actually never done this. This is an untested lab. I've never ran it on a cluster of this size. Under two, like if I run it again, can I get it to be under a second? Yeah, under a second with 16 executors. How long did it take on the smaller executor? Even in a smaller executor, you can go through it in under a minute. So this means that when you guys go back later, what I'm going to do is I'm actually going to terminate all of your small clusters and leave 2 community clusters in each shard. There's 3 shards. I'm in shard 1 right now, 0, 1. But you're in 1 or 2 or 3, and in each one of those will be 2 community clusters with 4 workers each. So you'll be able to go through this data in probably a quarter of a minute. Full scan in memory of all of English Wikipedia. Now keep in mind, if you start doing computationally expensive things, it won't be half a second, right? If you start doing things like PageRank or expensive machine learning, those multiple iterative algorithms that have to do multiple full scans on your data, it will take a bit longer. Okay, I'm going to register the temp table of Wikipedia so that I can answer my first question. What percentage of Wikipedia articles were edited in the past month? So I'm looking to understand how fresh is Wikipedia. So technically this data is from October 5th, 2015. Let's figure out how many articles were last edited between September 5 and October 5, 1 month since the time of this collection. Okay, SQL query, very simple one. This many. So what is that? That is 686,000, approximately 700,000. So that is what, like a fifth of Wikipedia is less than a month old. That's pretty interesting. Oh, actually, I did the math wrong. It's like 11%. It's still very impressive. Here are some of those fresh articles. Maybe you wanted to only analyze things that were touched in the last month. I mean, imagine you can also say, what are like the articles that have not been touched in 5 years, and try to understand why have they not been touched. But we won't do that right now. Next question, how many articles in the current snapshot that I'm playing with were last edited by ClueBot NG, a anti-vandalism bot? This user is a bot. Anti-vandal bot that tries to detect and revert vandalism quickly and automatically. Made by these people. What does this say? ClueBot NG, all this like machine learning stuff, false positives, vandalism detection algorithm. So it looks like there's machine learning bots operating on Wikipedia live edit stream looking for vandalism using neural networks. All right, well, how active is this guy, this robot? $21,000 articles. Let's run this command. Let's look at some of them. So I can take this revision ID on the Patrick Taylor article, and I can do something kind of interesting with it. 1 second, let me pull up the URL to do this. Okay, so I'm not sure how I can do this. Wiki, yeah. So this is the URL. You might want to. Well, this will be on YouTube, so you can do this later on your own time. But what I've done here is this article. I'm not sure who Patrick Taylor is, but ClueBot reverted somebody's edit. Maybe because it was vandalism, and I want to know what this was. What did he do? What did he revert? So you just go to that revert URL. Somebody put in, Pat is wonderful and making stories up. That doesn't sound very much like something I would read in an encyclopedia. Wikipedia is supposed to have a principle of policy of neutrality, so unbiased and fully sourced. You're not allowed to have any original analysis in Wikipedia. Everything has to be sourced out to other authoritative sources. This certainly does not look like an authoritative source to me. So Cluebot somehow found that and reverted it back. So he did not allow this edit to happen. And you can see other articles that Cluebot reverted back. He basically didn't, as soon as the edit happened, it got stored forever in Wikipedia's corpus, but then Cluebot did a revert to that edit, which also got stored in the full 10 terabytes of Wikipedia edits. So actually, there are a lot of bots maintaining Wikipedia. Before I even do this, let's run the next. Okay, I actually have a link for how you can find their revisions so you can study them for yourself. Interested in learning more about the bots that edit Wikipedia? So there's a lot of bots actually. This bot did this many edits. Now, this many edits historically forever. So I'm not talking about just this current snapshot. Because when I look at my snapshot right now, I can only see when was on this static page copy. This was the last time it was messed with, basically, edited. But what this is talking about the 10 terabytes of edits, which we're not really analyzing in this class. That is something that we aim to analyze in our 3-day class, to actually derive machine learning models off the historical 10 terabytes of edits, and then based on what we learn, apply those models to Spark streaming in real time to see if we can actually make a better, perhaps anti-vandalism bot than Wikimedia. I doubt it, but it'd be a fun exercise. So there's a lot of bots. I didn't actually know that there was an army of artificial intelligence bots that were sniffing the live edit stream and doing all sorts of maintenance work, essentially defending the integrity of Wikipedia. What's our next question? Which user in our October 15 snapshot of Wikipedia was the last editor of the most articles? So a really ferociously active editor is what we want to find. Let's see. Who are the editors? This bot touched, in our current snapshot, he touched this many. Wow. Bot. These are all bots. So even though we're looking at a static copy of Wikipedia right now, there's bots all over it doing things in it. They're quite active in maintaining Wikipedia. So bots don't create the articles, but they do a lot of interesting things. For example, back in like 2012, somebody wrote a bot that would read the US Census data to understand where all the cities are in the US, and then automatically create a page in Wikipedia that would say things like, this city has population of this many, this type of store, and like everything it could get publicly from an authoritative source. So what happened pretty early on in 2012, this was controversial. It was the first time a bot was applied to create articles in bulk. But basically what happened, if you look at the curve of the early growth of Wikipedia, it suddenly went like that. And then it kept going, because that part was made by a bot. So if you look at the article creation, or if you go back to the 10 terabyte edits, you can capture stuff like that. Can you display the titles of the articles in Wikipedia that contain a particular word? Display the titles of the articles that contain, so I want to give a word, and then I want to see if that word appears in the article body. If it does, give me the title of that article. So let's make a UDF to do that. I'll let you skim through the code. So I made a UDF, and then there's this feature in Databricks called parameterized queries. And with parameterized queries, I can get this type of box and then type in Amsterdam, for instance. And there we go, less than a second. These are all the articles that have the word Amsterdam in them. Or how about Hadoop? Let's see if it makes sense, the results we get back. Yeah? What are the top 10 most common words in the English language? Well, to do this, I'm going to have to do word count on the articles, but you know, the article text is a little bit sloppy right now. It has, you know, if you want to look at what the article text looks like, let's go to the Apache Spark page. And if you click on Edit, you can see that the text has a bunch of stuff. It's not like there's like this other language here, like a formatting language that appears. So look at this. The words machine learning and algorithms have like double brackets. Where is, okay, here it starts. So open source software and open source both have these double brackets. Software framework, AmpLab. Okay, I'm going to go back and look at the article, the live article, and try to figure out why are there double brackets around AmpLab. So let's go back. AmpLab. Oh, that's a link. So a link in here is denoted by double brackets. You can also go to View History and see all of the historical edits that built up the Apache Spark article. And actually, Blue Plastic is my username. So I can click on this. Actually, I want to compare it to the previous article. What did I do? I added +, this sentence to the article. So there's basically a full history of everything that's ever been done. And anyway, the article text was a little, had all those formatting characters, so that's what we're doing here. We're basically cleaning it up with the UDF, and then we're calling that UDF. Actually, first we're just selecting out the word and the count from count words. So here we're making an RDD called count words. Notice that I'm dropping out of the safe, fast, and structured API of data frames down to RDD level because I need to work with unstructured data, and it's much easier for me to express my computation in RDDs. So that's what I'm doing. Then I'm going back to a data frame. So actually, this might have been done incorrectly. Like this might have, I think this might be actually a data frame, not an RDD. Actually, no. Then, okay. Well, anyway, we want to move fast. We're not going to get caught up in those details. Let's just run this. What did we get? Off, the, in. Yeah, I guess that makes sense. Those the and off would probably be like the most common words in the English language. Okay, it makes sense. These could be stop words that you use in machine learning models to basically get rid of these words when you do things like TF-IDF, for example. Can you extract out all of the words from the Wikipedia articles? I would ask you to hold questions until later, until we do Q&A. So here I'm making a tokenizer to yank out words. And then let's see if this worked. From wiki words data frame, select article and words first. Show me the first one. Yeah, that looks right. Like it kind of worked. It looks like it got all the words. So then let's see it like this. It's a little hard to read, but basically there's a new words column now with a bag of words. Yeah, I guess we could do display, but you would see the same thing as above this. Hold on, let me refresh this, sorry. I think when I make the screen really big like this, it sometimes becomes hard to follow. Okay, we're almost done actually. That was it. What was this? Display, yeah, I guess I did that anyway. Yeah, so this is the same table, but I added on another column with an array of words. Let's see if I can open this. Right, so I just put like all the words in there. So I was basically preparing this data set for more serious machine learning by trying to extract out everything, make sure I had all the words separate to be able to do things like TF-IDF. All right, so that concludes the Wikipedia example. And the thing that is going to be really cool that I'll give you some time to do some hands-on work on is GraphX. So I've been working at Databricks for about a year, and we do pre-class surveys before every class. And GraphX really gets no love, even from you guys. So I asked you which project in Spark were you the most interested in learning today. And like always, GraphX comes in, it's kind of sad, under 25%. But I think you're missing the power of graph processing. So I'm going to try to convince you that graphs are not to be ignored. And it's actually really simple to think in a graph way as opposed to a table way like data frames allows. So in the next, how am I doing on time? Because we have to do graphs and Spark streaming. We have 2 hours and 45 minutes. Actually, no, 1 hour and 45 minutes. So that is actually great because I think we can cover both of these. So let's talk about graphs. I'll give you the theory behind graphs in the next 10 or 15 minutes. Then we will start crunching through the clickstream data, but from the perspective of graph processing. All right, so this is how graphs work. Here I have a vertex for Amsterdam and a vertex for London and an edge, a connection from Amsterdam to London. Maybe the Amsterdam article has referred someone to the London article. So someone went inside Amsterdam, clicked inside there on a link that sent them to the London article. So this is how we're going to start making a vocabulary and a terminology to build upon for GraphX. So vertex and edge. Edges are connections. Vertex are basically the nodes, the items in your graph. Now, you can have many different types of edges in graph engines. You can have a unidirectional edge, which is how GraphX operates, a bidirectional edge. You can have two unidirectional edges, which almost kind of like signify like a bidirectional edge. So those are some edge types. GraphX itself is a directed multi-graph. So you can do directed edges. Each one of these edges has a forward-pointing arrow. There's no bidirectional edges here. But you can kind of get the idea of a bidirectional by just doing back and forth. So two edges exist. You can actually build even 50 or 100 edges if you want between these two nodes or these two vertices. So to get a little bit deeper, you can put IDs. Actually, you have to put IDs on vertexes. And then you can put labels on edges. Now, maybe your label will be a weight. In this case, it is a weight, meaning 22 times somebody went to this article and then clicked onto London. But in GraphX, it's just a label. You might want to treat it as a weight in your computation, but it's a label. And vertex ID is a long data type. And each vertex also has a label. In this case, perhaps the label is a string or a string for that vertex. So if we then look at our graph with labels like this, like the number 22, then here's the same graph you looked at before, the directed multigraph with labels. So let's do a quick algorithms tour of GraphX. In degree, if you call in degree on the vertex Amsterdam, and if this vertex has pointing to it, incoming, 1, 2, 3, 4, 5 edges are incoming, then the in degree is 5. If, for example, let's say 2 edges were going out, the out degree would be called 2. We're not looking at weights or labels at all on the edges. We're just looking at how many incoming arrows there are or outgoing arrows. So in degree here is 5. PageRank is somewhat similar, but in PageRank, we let the node here, for example, gets to vote on the Amsterdam article. And since he's a highly influential article, his vote counts more, versus in degree, it does not. But in PageRank, it does. So here's PageRank. Let's see, if we want to do PageRank on that red node, 1, 2, 3, 4, the in degree is 1, 2, 3, 4, then each one of these nodes here, 1, 2, 3, and 4, are going to be able to vote to decide how important he is. Okay, so then we just sum up the votes. So that's what we're doing. Everybody's voting. The sum up of the votes was 3.65. So this happens in parallel and at scale in PageRank. And actually, PageRank is, I'm sure as you might have heard of it, because it's the famous algorithm that Google invented for search. And the name PageRank actually is a play off of the name Larry Page. Okay, that was PageRank. Shortest path, another algorithm that we will look at in lab. We're actually going to look at all of these algorithms in a few more minutes in lab. I'm just trying to get you the theory of what's going on. Shortest path. So maybe I want to know what is the shortest path from this vertex to that vertex. And when I look at this, it's kind of confusing. I mean, I don't really know what the shortest path is. I mean, when I want to go from here to there, there's really only 2 possibilities to leave this node. These other 2 black ones are incoming, so I have to go either that way or that way. If I go to the right, then I can go up. Then I can go either this way or that way. Right? So you can imagine that there's some computational complexity here in trying to figure this out. If I go that way, there's 5 hops. 1, 2, 3, 4, 5. But if I go to the right, the shortest path is 1, 2, 3, 4 hops. Right? So you can imagine that perhaps what you might do is, this is the Amsterdam article, this is the Apache Spark article, and maybe you're trying to find what is the quickest way I can click through Wikipedia to go from one to the other. So this is the mathematical way shortest path works. I'll skip through that. Now, this is an interesting graph. Look at this for a little bit. There are 2 types of vertices in the same graph. Another thing that is perfectly fine in GraphX. But when you look at this, can you tell me what is special about the red vertices? So just yell it out if you can figure it out. Yeah, exactly. So all the reds only have out degrees, no in degrees. There's nothing coming into the red ones. What could this be? What in the real world might make a graph like this? I don't know. I mean, if you think about eBay, that is shoppers and buyers, maybe what this means is, like, this guy bought something from him. This guy bought something from 3 people. This guy bought something from here. But this guy, he bought something from him, but he also sold things to this guy and that guy. So by yanking out a subgraph of people on eBay who only tend to buy but don't sell, perhaps I can do some special type of marketing campaign or email campaign to convince them that eBay is also a good source to sell their old used goods. Simply by looking at the in count and out count, I can figure that out really easily, actually. You're going to do this in the lab in a few minutes. It's one line of code. A lot of what machine learning and graph processing and Spark does is it black boxes these algorithms, so you don't need to know the math. You just need to know the concept that you're wanting to do, and then you just call the method that's going to do that concept, as you'll see. So our goal is to simplify and demystify graph processing and machine learning. And graphs are everywhere, and I will convince you, hopefully, in the next few slides. Here is a graph of social networks where users are represented by the nodes, the vertices, which are connected by edges, and the edges represent different labels. This edge means he likes this post. This edge might mean that he uploaded that picture, right? So the edges can be different things. So anyway, this is a very common social graph. Look at this one. What do you think this is? This is an example of a web graph of political blogs and links between them. You can see that when you look at it from this perspective of graph, that they cluster strongly into liberal and conservative blogs. So here, the edges are the links between the blogs, and the vertices are the web pages. This type of insight is really hard to come at when you just use SQL or data frames. You have to kind of break out of that world and have yet another paradigm of programming. Look at this. An illicit, illegal kind of network and a legal network. What is this? This is the Enron email graph, where the vertices are users, employees at Enron, and the directed edges here are emails to, from, and to. Notice that there was a cluster of people at Enron that worked very tightly together, perhaps. So the graph here, essentially, the email graph of Enron looks like a hub of informed people. A hub of informed people with spokes of outsiders who are too isolated to figure out the illicit behavior. But in a healthy company, there's a lot more communication across the company. Look at this one. This is a Bitcoin transaction network trying to uncover and reveal the anonymity of the different users using Bitcoin, where the vertices are the people and the organizations, and the edges are the exchange of the currency of Bitcoin. You can go to this blog here to understand more about how this was derived and what this means. A very common graph is this one. This is when users rate products on sites like Amazon or Netflix. This vertex has a label of 5 for this song. And this user also really loved his telescope. Right? So recommendations. Look at this. This is a graph created by the Nieman Journalism Lab using Wikipedia articles. This shows a network of articles in red. Those are the big red dots. And the editors who contribute to the network in gray. Within the first 4 hours of the article's existence. So imagine that what happened here is somebody basically extracted out all of the edits related to school shooting articles. So one thing that happens in Wikipedia is when a live event happens in the world, about an hour after that event or so, an article gets created for that event. And this is showing what the network looks like 1 hour since the point of creation of articles that have to do with school shootings. So these articles were all made at different times, but if you normalize all those times to be starting at the exact same vector and then move outward 4 hours, this graph was created with that in mind. So imagine that we are looking at what the network looks like 4 hours after these articles are created, and we can see these little people around it. So this looks like a flood of people come and edit these articles. This guy actually edited both articles in school shootings before the first hour. Look at this guy. He is a specialist actually in this field. He seems to, whenever a school shooting happens, be active in the creation and editing of these type of articles within the first 4 hours. So this is something that does happen on Wikipedia. There are these volunteer editors who specialize in things like earthquakes or whatever their field of interest is. But what changes is this was created 4 hours after the article was created, but 6 hours after the article, these are the same articles. 6 hours later, it becomes like this. 48 hours later. So this is a very different picture. Same articles, 48 hours later, but this is 4 hours after the creation. What's happening here is that it seems that in the beginning, when the article gets created, everybody edits it. A whole bunch of random people come and edit it. But essentially what happens is 48 hours later, there arrive to the scene these specialists who, from that point onward, basically take over the maintenance and the curation of that article. So in the beginning, it's a little bit chaotic. And 48 hours later, you can see that there are indeed way more editors. However, there's these really dark, stronger lines. These are the people who are essentially controlling that article, making sure there's no reverse they don't like, or no edits they don't like, I mean. See, here, there's not that many dark, thick lines. I mean, there's this guy, he arrives early. But here we can see more actually of these thicker lines. So that's what we're seeing here basically, that the structure changes 48 hours later of the graph. Check this out. This is from the Wikimedia Foundation. And let me explain what this is first. This graphic image, this graph network illustrates the interlacing of SOC accounts. Wikipedia gets very coordinated attacks from rich PR agencies and even state-level attacks. And they're trying to influence these articles. So what Wikimedia Foundation discovered is this is a recent graph. This is like 2 months old. They extracted out all these people and they removed them from the allowed editors list of Wikipedia. The yellow bubbles represent IP addresses, and the green bubbles represent accounts. Following an investigation, about 2 months ago, 381 accounts were banned from editing Wikipedia for working on paid articles without disclosure and also extorting money from users. So this is a investigation that's nicknamed Orange Moody, M-O-O-D-Y. Basically, what Wikimedia Foundation's data scientists discovered is that there were a lot of sock puppets being created. And what a sock puppet is basically is when one human makes 15 different accounts and then uses them in coordination to leverage influence on one article. So they extracted out this entire racket of sock puppets and banned them. Okay, another example of graph networks, belief propagation, predicting user behavior. On the left, we have a user, and on the right we have a user, and these guys like read blog posts. This guy, though, is liberal, and he tends to read liberal blog posts, and this guy's a conservative on the right. Now, perhaps we know about other conservative users, and we know about other liberal users, okay? So we don't know just these two people, but we know other people. Like, this guy's a little confused, I guess. But, okay, well, look at these people that just arrived. We don't know about them. We don't know if this guy's, he has never actually, perhaps what this whole thing is maybe we own medium.com or a blog network, right, like Blogger. And we know that, like, this user, when he logs in, tends to always read liberal articles. This guy, when he logs into my blogging website, he tends to read conservative articles. And I know about some other people who use my website as well. But here's the thing. These people, maybe you don't know about at all. But if you look at this from a graph perspective, so what did I just do there? Well, I know about these people, okay? So, like, for example, I know that this guy's red, he's blue, okay? So red and blue. So this is red, this is blue. Now, this guy knows him. They're like friends. And this guy knows him as well. But, this is how we can do basically belief propagation. We can start saying that, these are the, we're predicting that he's liberal because he's friends with him. Now, these guys are kind of like middle of the road. They're around neutral people. So this way, by projecting a graph relationship upon our visitors, we can essentially try to classify them as liberal or conservative. Something that would be very hard to do if you didn't look at this from a graph perspective. Okay, with that being said, I would like to now switch over to the GraphX lab, and then after that lab, I will have one last GraphX page for you, one last slide on GraphX, and then we will basically move into Spark streaming. So let me cover what we're going to do in lab, and then we'll come back and do one extra deeper analysis of how does Spark actually make graphs. Spark Core only works on RDDs. Data frames translate down basically to something like RDDs. This will change most likely in the future in Spark. There's some new changes happening, as you'll hear about later this year. But for now, everything usually goes down to RDDs, especially in GraphX. Anyway, we're going to revisit the clickstream data. Remember we looked at it like this before? Refer resource. But what if we instead looked at it from a graph perspective, where instead of saying Google is going to be seen like that, what if we said the fact that Google sent a lot of traffic to London means Google should be a larger bubble than the other Wikipedia article. So now we're saying Google referred people to the London article. And then from there onward, people went to either England or UK or City of London. Okay, so to get this started, what I was planning on doing is a short demo first of GraphX to get rid of all the complexity and just really quickly build a graph, do a couple of things on it, and then we can actually do the normal lab. All right, so we do some imports. And I'm just going to build a fake graph first. I just want to show you how easy it is to do. I need to make a vertex first, a vertex type. So long and string is our remember, a vertex is like a node. This is a vertex. A vertex has an ID of long, and then it has a value. The value can be whatever you want it to be. The value can be a string. In this case, though, the value is, actually no, it is a string here. So here we are saying that the vertex is 1 or 2 or 3, and the value is the city for that vertex, like the pretty print way of looking at it, the human way of interpreting the label on the vertex. Okay, so we have the vertexes now. Now we need to make the connections. That's what we're doing here. We're saying here that the one ID, San Francisco, is linked from 1 to, what is that, 3, Tokyo. So basically, San Francisco points to Tokyo, and this edge has a label of 10. What does that 10 mean? I'm not sure. Maybe it points to that 10 times. This is not a weight, it's just a label. You can put a string there if you want for the label. Anyway, I make my vertices, I make my connections, my edge, and then what we do, I need to run this cell. Okay, I need to run this one too. Okay, we have all the vertices and we have the edges. Next, we make a graph. To make the graph, we just pass in the vertex and the edge. Actually, we took up there, we were making arrays. We converted those arrays into RDDs, vertex RDD and an edge RDD from the edge array. Then we just pass those two things in and we get a graph that I'm going to call G. How many edges are in here? Well, I mean, look, if I go up here, 1, 2, 3, 4, 5, 6. How many edges are in my graph? 6. How many vertices? I think it was like 5. 5 cities. In degrees on G. 4 has 2 going in. So the ID of 4 has 2 things going into him. We can go up here and check who 4 is, but let's move fast, so I won't go and do that. You'll do that in lab. You can check out degrees. You can yank out a subgraph of just Tokyo, or you can do something more sophisticated and say, pass in like some regular expression or something and say, yank out a subgraph that matches this, right? I was trying to do like PageRank on the Wikipedia data set like last night on the smaller cluster. So like you guys can load the entire Wikipedia corpus in your small 30 gig cluster, but doing something like PageRank on that is so computationally expensive. It needs like tens of thousands of tasks. And you can only run, like 4 at a time. Those finish, then 4 more, then 4 more, 4 more. I tried to do PageRank and it just ran for way too long. I stopped it after like 20 minutes. So you would have to pull out a subgraph. And then on that subgraph, you can do things like PageRank, unless you have like a really big cluster. On my subgraph here, I got a subgraph that's like really tiny. It only has 1 vertex. Yeah, so I didn't pull out a full graph. I really just pulled out one thing. On my graph, though, I can do PageRank as well on the actual graph of the cities that I built. But look how simple it is to do PageRank, essentially, and you'll learn what this means in the lab. So now, which one has the highest number? The first thing is the vertex ID, 4. So this is 3, 7, 3, 8, 2, 5. So 3, 8 does. Whichever thing is 3. What's 3? 3 has a lot of things going into it. 1 and 2. Yeah. I guess, anyway, PageRank gave this a higher rating, but notice that 4 also has 2 things going into it. But remember, PageRank doesn't just look at the in count. It's also looking at the influence of this. So PageRank gives us something more sophisticated than just doing a trivial in count. But I'm just trying to point out in this demo how simple these things are to do. What about shortest path algorithm? This is my shortest path. So now when you do shortest path, I can see that for each one, what the shortest path is basically, and you'll learn how to interpret this as well. Okay, I think that's all I had for the demo. Next, I'm going to introduce you to the GraphX lab, maybe do the first part of it really quickly, and then let you play around with it. Okay, what's going on here? We did that. GraphX, clickstream. Let's do the run me version. You know what? To make things be fast, I'll attach this time to my large cluster as well. And then I will definitely let you guys play around with this for a little bit. Okay, that's the one with 16 executors. So look at some of the questions we're going to now ask to the same clickstream data that we looked at before. We start with something very trivial and small. We'll do triplets view, in degree, page rank, pull out a subgraph, and do a shortest path on it. And actually, I also wanted to then graph the shortest path using d3.js, which you can also do, but I just didn't have time to build that out this week. But maybe as a homework assignment, you could try to see if you can figure out how to do that. If you go to Databricks guide, there are some examples of how to use D3 visualizations in Databricks notebooks. Here are some of the technical accomplishments for this lab. Okay, once again, like always, I will walk you through the first little part of the lab, then I'll let you hack on it yourself. Okay, so we'll get some imports out of the way. This is just covering what I covered in lecture, so it will then make you start thinking about the same data in a graph perspective. Let's make a data frame first. Clickstream data frame. I like to, if I have structured data, I like to start always with a data frame, because data frame has really these nice handy read functions that makes it really easy for me to like infer the schema automatically, as opposed to like doing that manually with the RDDs. So I like to always start reading structured data with data frames, and then I can convert the data frame to RDD if I want. Here what I'm doing is I'm going ahead and caching the data frame. Then let's run show 5 to make sure that I did read it successfully. Now, technically, if you have a 16 worker cluster like this, all the data sets you've seen today so far, you can actually load in memory and then do joins across using these different programming paradigms. I actually did some math last week to try to figure out how much it would cost to crunch through the entire 10 terabytes of edits. And if you're interested, if you launch a 64 worker or a 64 executor cluster in Databricks, if my math is correct, if you launch a 64 worker cluster, then you can crunch through, do a full scan of the 10 terabytes of edits in under 15 minutes at a cost of under $3 for each full scan. So don't quote me on that because I did that very, very late at night. But we are planning on doing things like that in our more longer 3-day class that builds upon this. So if you're interested in doing machine learning, deeper machine learning, and things like that, then check out the Databricks training page. Anyway, this is the same thing that we did in the demo. We're going to make an articles RDD, then a connections RDD, combine the two into a property graph. So that's just all we're doing here, basically. We're pulling out from the data frame. This is the exact same data frame from the earlier lab, clickstream data frame. We're pulling out these two columns distinctly that we need to make the unique articles data frame. And then on, let's look at what the first 10 items look like in the unique articles data frame. Okay, there we go. That looks good. Next, okay, so I won't bother showing you that in memory. How many articles are there total? We haven't even gone into graph or anything yet. We're just kind of getting everything ready right now. So there's like 3.1 million, I think, if I can read that correctly. And then the clickstream, okay, yeah, 3.1 million unique articles. In February 2015, that many unique articles were requested from Wikipedia out of like the 5 million that probably existed, roughly 5. We need to make an articles RDD first. This is a vertex RDD, so you can convert a data frame to RDD like this, .rdd, and then we take 3 elements out of the RDD, and you do take, you get an array back. Article title, article ID and article title. Article ID and article title. So this is how easy it is to just move back and forth between data frames and RDDs. So then on the unique data, we get the RDD, and then what are we doing here? We're just printing this out. That, okay, so this is not really making anything yet. What are we doing here? This time, instead of printing it, we stored the transformed objects in a new RDD, articles RDD. And now we have the articles RDD. Let's take 3 things from there. Perfect. This can be used to be the edge RDD basically, because we have edge ID and like an edge label, which is in this case the article title and article ID. Next, create connections. So we need to make an edge RDD. So on the same data frame that we used earlier, we need to somehow figure out that, you know, this ID referred to this ID, but notice the nulls here. This is not going to look clean in a graph, so I need to get rid of the nulls. So I'm going to drop out the null values. That's better. Then select out the 3 columns needed to make the edges distinctly. ID, ID, and then the label on the edge. Finally, we're ready to create the edges RDD. And let's just take 3 things out of it so you can see what's in it. It's going to be what I showed you above. This article requested this article 30 times. There we go. Finally, we make a graph. So we're going to call it the clickstream graph, and we just pass in the 2 RDDs we just made. And now we have a clickstream graph being created. There it is. So like RDDs, property graphs are immutable, distributed, and fault tolerant. Changes to the values of the values or the structure of the graph are accomplished by producing a new graph with the desired changes. We can extract out just the articles and just the edges separately from the graph if we want to. So you can do like this, like just pull out the vertices, take 3 of them. So we're pulling out the nodes or the articles only, 3 of them. And there we go. So you can get just the vertexes, article ID and article label. That was kind of slow. Yeah, let's cache that graph. And then next time we do a full read, that lazy cache will be materialized. Here are the edges, just 3 random ones. How many nodes are there in the graph? How many articles? It was what? About 3 million. Here's another way to do it. Number of vertices is about 3 million. How many edges? How many edges are there between those 3 million? Much more. 14 million connections. All right, this gives you a sense of the computational complexity of our graph. Okay, I'm going to let you guys do these questions. So I'll let you hack on it for a little bit now to get your feet wet. It's 3:50 right now. This is a cool lab. I'll give you 15 minutes to do it. So it's 3:50. We will resume at 4:05. And what I'm going to do is I'm not going to give you guys another break because I do want to get through streaming. So what we'll instead do is we'll do this for like 15 minutes. If you need to use the restroom, now is the time to do it. But please don't consider this a break because I'm going to start exactly at 4:05. So you're probably better off getting some experience here. And then we're going to just quickly jump right into Spark streaming, connect to the live edits, and then we'll conclude. And we'll probably conclude around 45 minutes from now. And then we'll turn off the YouTube recording and then do Q&A for about 20 minutes. All right, so good luck with this. I'll come back to revisit this as a short conclusion to this lab in about 15 minutes. So before I go into the rest of the GraphX lab, I wanted to show you and give you some intuition of how graphs are represented as RDDs. On the left there we have a property graph. This is the graph we just made in the lab. There are vertices of A, B, C, D, E, and F, and then we can see the edges in red. So what we do in GraphX is this. We take those vertices and we make a vertex table out of it. This is a vertex RDD essentially, where the first partition has, this is an RDD with the first partition having 3 vertices. Second partition of the RDD has 3 different vertices. So we've extracted out the vertices. I mean, that's kind of relatively simple to do, but what about those edges and where do you cut the graph? So in GraphX, we do vertex cuts. We cut the vertex like that, and we break apart the graph into 2 parts. Notice here that the A vertex now has been split into 2 different partitions, where when we represent the edge table, A to B is going to be in the edge RDD's first partition. A to C is also there. But A to F is in this other partition. A to E is also in a different partition. Now, this is interesting. What we are trying to do is make sure that this vertex is not split up into too many different partitions. Because at least now, to operate holistically on the network around A, we only need to read 2 different partitions, basically. These 2, and actually, no, not these 2, just this one and these 2. So from this RDD, we have to read basically 2 of these partitions, right? Because A is in both of them. So we have to read some subset of these 2 partitions. Here, we just have to read one of them. And what happens here is we can see A is going to all of these. We have a routing table. This is an internal RDD that that GraphX makes that you might have not known about. And this internal RDD has a routing table saying that A is in partitions 1 and 2. B happens to be self-contained in partition 1. So we go and look at in this routing table, like for D, we need to actually read in edges for D from both partition 1 and 2. Right? So this is how Spark works when you do graph processing, kind of behind the scenes. Okay. So now I would like to finish up the GraphX lab really quick and then get into Spark streaming. And then we will conclude for the day. All right, so I had left off here, actually a little bit higher up. Okay, so here's where we left off. Can you confirm that there is an article about Amsterdam in the graph? So to do this, we're going to start, playing around with data frames and graphs. So first, actually for this though, we don't need data frames. We're just going to say on the graph, get the vertices. This is actually an RDD, so we are actually playing around. When you call this, you get an RDD back. How do I know? Remember, you should feel very comfortable doing this all the time. Break apart your code into smaller segments. That gave me a vertex RDD. On that, I'm going to filter where I'm using a Scala case class here on article equals Amsterdam and then count. This will come back with 1 equals true. Apache Spark is also there, so I just changed the name to the word to Spark. If I change this to something else, you get 0. That's just confirming that the graph is healthy in some ways. How many articles in the graph have the string Amsterdam or Amsterdam? So now I'm going to show you how to how to identify with the regex. So I'm going to declare a regular expression right here. that is looking for capital or lowercase a. And we're gonna apply the regex to this string, and hopefully it'll get both of those Amsterdams. Test it. It worked. It worked locally in the driver anyway. Now I need to apply that to the graph. So this is the pattern, and now you'll see that this is how I'm doing it, and then I'm counting. I wonder how many I'll get back. Anywhere in the title, it can have upper or lowercase Amsterdam. 336. Quite a bit. Which articles refer to which other articles and how many times? Triplets view. This is vertices, edges. Triplet says this refers to that. And how many times does it do it? So if you call 20 on that, it's hard to read. I'm just going to use some Scala to print that better. So I'm still just taking 20, but I'm just using some Scala to pretty print it. Anarchism refers to anarcho-feminism 73 times in the clickstream data. Which articles have the highest number of articles referring to them in degree? This one is super simple to do. This is how you get the in degrees on a graph. It's just one method. You can take 2 out of that and just see that we're getting vertex RDD back, or actually we're getting this back. Let's just look at what's in degree RDD. It's RDD. So then which articles have the highest in count, meaning which article ID, comma, in degree pairs have the highest value for the in degrees. Okay? This is how you do that. You get the in degrees array, and you'll notice we're getting article ID and in degrees, but I have no idea what article ID that is. So I need to do a join. Remember, if you still have this original data frame that we started this lab with, and this thing maps IDs to titles. Somehow we need to join this with the stuff we extracted out of the graph, this vertex ID. So we'll convert the unique data frame, unique articles data frame to an RDD, take 3. So we have to basically, RDD is the common language here. So we're converting the data frame to an RDD. From the graph, we're getting the vertexes, and then we're going to join. Okay. I'll show you that code right there. There we go. Okay, in degrees array. So we're basically, now we're actually going to join. And you can play around with this later and see what it does, and let's do a pretty print of it. There we go. So main page, it would make sense that main page would have the most things coming in, referring to it. Everybody refers back over to the main page. But then the US, there are a lot of articles that are pointing towards the US article, or the Internet Movie Database article, or the UK article, or the India article. So this vertex, India's in degree, is about 20,000 different articles are pointing at him, or not pointing at him, I'm sorry. This is from the clickstream. So in February 2015, that many times somebody else pointed to India. We're not taking the n into account here, like the weight. This is just in general, like a distinct point. Okay, what are the most influential articles? So let's do page rank. In 2015, February, it's really simple. I mean, just say graph, page rank, run. Well, this is the result, so you're passing it in the clickstream graph there. with 3 iterations of PageRank. So, I mean, it will probably be somewhat similar to the in degrees, but in degree it said main page US movie UK India, okay? Main page US movie UK India. Let's do the join and everything here too. Convert the RDD to an array. Join these two so we can get the title looking correctly. Let's see the results. Main page, movie, US, British, India. I mean, it comes back the same, but we can start to think about why, right? It's somewhat similar, but if you keep going down the list, it would probably start diverging. And actually, the weights will be very different from PageRank versus in degree, because this is like actual influence. What does the graph of connections between the top 7 most populated cities on Earth look like? So I'm going to pull out a subgraph. So the way I did this is I first went to this Wikipedia article of the most populated cities in the world, and I just like got the top ones, top 7, and then I'm running this code to first get the triplets of the view of the subgraph. Oops, I didn't make the subgraph yet. Cities graph. Let's see. I must have forgotten to have run something up here. Was it, which one? City subgraph is there. Okay, so we have that. I just might have a typo what I called it later. City subgraph vertices count, 7. Edges count, 36. Print out the, I just had a typo, I think, here. Oh, no, it worked. Okay. So this is it. Delhi refers to Mumbai that many times. That would make sense. So we pulled out a subgraph, and now we're kind of like looking at it in a almost like a tabular way here. Okay, and then what was the last question? The city subgraph, what is the shortest path between Shanghai and Mumbai? So this is such a small graph that it might not give us anything too interesting back, but this is just a proof of concept that would work even on your small cluster. I didn't get to play around very much to see how much data you can actually bring into a subgraph, and it would still run on that 21 gigabyte executor. Shortest path. So the way you read this is for here to get to there, it was 1, I believe. But remember, this is a tiny, tiny graph of 7 different cities. We'd need to maybe do it for 100 cities and then try to go between cities and see if that would give us something more fruitful. The last thing I wanted to just show you is like how you can do SVG printing within our Databricks notebook. And unfortunately, I don't have the D3 example in here, but I was trying to build out like get a larger subgraph. So here's a homework assignment. Try to get a larger subgraph of something interesting using all the tools you now know. And then on that subgraph, do a shortest path and then visualize it in D3. Right, so that was kind of the goal there. Okay, so we are getting close to 5 p.m. We have maybe another 25 minutes or so, which is, maybe 30 minutes, which is perfect because that's how much we need for Spark streaming. So I want to first ask for a show of hands for how many people here have used Spark streaming. So raise your hand. Wow. Okay, quite a bit. Maybe that's maybe 20% of the audience has used Spark streaming before. So let me do a quick review of the architecture of Spark streaming, and then we can jump into some of the details in the lab for Spark streaming. So this is the cluster that we have been using all day today, the little 30 gigabyte cluster that each one of you has. with the 21 gigabyte JVM, as you know, your cluster has 4 slots. But when you use Spark Streaming, you will launch a long-running receiver on one of those slots, leaving the other 3 free for processing RDDs. And what will happen now is in Spark Streaming, you can set a batch interval. We're going to set it here to a little bit more than half a second. So we'll set it here to 600 milliseconds. So now what will happen is Wikipedia is going to send data to this receiver thread, and in the first 200 milliseconds, whatever data comes in will make a RDD partition. In the next 200 milliseconds, whatever comes in will make another RDD partition. Basically, there's this setting internally that's set to 200 milliseconds that just says every 200 milliseconds, create a new RDD partition. You can change that if you want. And now that we got the third partition, so 200 milliseconds plus 200 gives us 600 milliseconds. We have hit our batch interval. Our RDD is now ready for processing. So now we're going to process it, and we basically are going to use these 3 slots. So imagine a red task, and a red task running there, and that is our processing latency. But as we're processing, more data is still coming in. So the receiver thread gets another partition for 200 milliseconds, another one, and now this RDD is ready for processing. So we would start processing that, and while we process that, we get another partition coming in. Now, the most important thing to understand about the architecture of Spark Streaming is you need to keep your processing latency less than your batch interval, or else you'll start falling behind. Because if the processing here took, let's say up to here, almost a second, then what would happen is you can only do 1 batch at a time. You cannot do 2 batches. It's like a first in, first out type of queue, like FIFO. So if the processing the first time for the first batch ended a second later, then what would happen is, even though this processing ends a second later, 600 milliseconds after the processing ended, 600 milliseconds after this batch was created, another batch is ready to go. But we're not going to be able to process this one until the first one finishes processing. Right? So because of this, we need to keep the processing latency less than the batch interval. So we need to make sure that this happens in our lab. All right? The other idea in Spark Streaming is of D-streams, discretized streams. So here, Wikipedia, let's say, actually in our lab, we set the batch interval to 5 seconds. So in 5 seconds, we build up this internal mechanism for an RDD. It's called blocks at this point. But then when the 5-second timer hits, our batch interval is now ready, and we then get an RDD, essentially, and then we can transform that RDD like with a filter. But what we're doing here is we're not actually applying that transformation on the RDD itself. We're applying the transformation on the D stream. What does that mean? Well, all that means is that every time we get a batch, we're just going to keep applying our DAG. So when you apply a DAG, a directed acyclical graph, to a D stream, all that means is keep reapplying my DAG every time a batch gets ready. That's what the difference is. In Spark Streaming, we have to initialize our DAG. We have to set up the directed acyclical graph with the chain of transformations before we start processing our stream. And I wanted to mention that data frames are coming to Spark Streaming soon. Maybe by the end of the year, or maybe early next year. Okay, so I guess I have something interesting to show you now. The live edit stream from Wikipedia that we're going to be listening to is going to be only to the English Wikipedia. And we're going to be, when I tested this earlier this week, we're going to be getting about 1 to 5 edits coming in per second. And we'll do a batch interval of about 5 seconds. So I'm expecting that in every RDD that gets created, there'll be maybe something like, 3 times 5, something like 15. Maybe like 15 edits every 5 seconds, roughly, is my intuition. So we've been like listening to this sound, and I wanted to show you what this is. So if you go to this website, so I'll put here's the URL for this. If you go to this, then you can listen to the melody of every edit coming into Wikipedia. And I'll mess around with this to show you this. So I'm going to make this a little bigger. First of all, you can see the edits coming in from either anonymous users, unregistered, or registered users, and everything is saying EN because I've restricted this to be, I've restricted this to be just English Wikipedia. So let me scroll here, upward. I can bring in other Wikipedias as well, but it would probably get more loud. Well, those Wikipedias are actually not probably very actively being edited. And then I can also do this, instead of hiding the graphics, I can make them appear again. And now we can see the visualization in d3.js. And technically, this would be doable in the Databricks notebook as well. We can embed this visualization in Databricks. I just haven't had the time to. So we can see what kind of edits are happening. BBC TV. And then I think it explains here like what all the colors and everything mean, and you can hide the graphics and play around with this. But I thought it'd be cool to show you maybe a couple more things. Hang on. This is another thing that I found that was pretty cool. So look at what we're going to do here. Okay, so now Wikipedia and Wikidata real-time edits. Actually, I don't want to look at Wikidata, just Wikipedia. So this is starting to grow out now. We're suddenly starting to listen to Wikipedia. Let me make this a little bigger again. So here on the left, we're looking at bots versus Wikipedians doing edits globally to all the 290 language Wikipedias versus, this is the English Wikipedia. I see, since I started listening, about 36, 40 edits happening, and they all seem to be happening by people, not bots. It's interesting that right now people seem to be actively there. Here, we're looking at anonymous users editing versus logged in humans. When an anonymous human edits Wikipedia, it does log the IP address, IP4 or IPv6, as you'll see in the lab. But when a logged in human does it, then in that column we get the username. So I can see that English Wikipedia is leaning more towards humans, I guess, but it's interesting to see that other Wikipedias sometimes lean a different way. For example, this language Wikipedia is leaning more towards bots editing it right now. Maybe it's going through some maintenance. And you can see that different languages have different characteristics. If you leave this running for a look at this one actually. Which Wikipedia is this? People tend to, well, there's only 2 edits that came in, so I can't read too much into this. But to whatever language that is, 2 anonymous edits. What is it, Turkish? I guess if I was there, I would probably anonymously edit it too. Okay, so anyway, because of these little visualizations I found, I was motivated to try to do something like that with my team at Databricks in the training department. on Wikipedia. Actually, I have one last visualization to show you that motivated our work. Oops, right here. This is a Wikipedia recent changes maps showing globally where the changes are happening right now. Let's see if we can see this and which articles are being edited right now globally. So we were thinking, how would we build this in Databricks? If you scroll down, you can actually see the changes that it's noticing. University of Malaysia, somebody in France edited this. If somebody edited with their username, we don't know their location. But if they did it anonymously, we get their IP address. This is a way to this is the only way the data scientists at the Wikimedia Foundation can defend against attacks on its corpus of text by keeping the IP intact. So anyway, this is the visualization that we are going to try to create right now in the next 15 or so minutes. So let me close out of this. And we'll go to the last lab for today, which is this one. And I'll go to the Run Me version again. I'll connect to the Samir Demo 3 cluster. So now I'm connected to the same type size cluster as you. And check this out. These are the questions we're going to try to answer. Oops. Approximately how many edits occur to English Wikipedia every 5 seconds? Anonymous versus authenticated users versus robot edits. Okay, so along the way, we'll learn a bunch of stuff as well. So we're going to do some imports. Now, once again, I urge you not to get too caught up in the details of what I'm doing. Try to get the intuition, because the details are relatively easy to figure out by looking at the Spark documentation. Okay, so we're going to run this cell and set up some, let me make this a little bigger, set up some things, specifically a streaming server host. So what we did is we are running currently a Node.js server, and that Node.js server is listening to an IRC channel. That IRC channel, it has the live feed of edits. I think the Wikimedia Foundation or somebody directs it into an IRC channel. Our Node.js server picks it up and sends it to Spark Streaming, or actually Spark Streaming listens to that Node.js server. I'm running here just NC, then an IP address on that port. And if I do that, I'm now not even using Spark Streaming. I'm just like using NC, the Linux utility. I'm just listening to make sure that on that port there are edits indeed coming in. But let me stop that for a second, and let me pick one of these edits, and I'm going to then pretty print it. So I can't really read, so I'm going to bring that back here. I'm going to pick one of these, and then we're going to stick this into JSON pretty print, just to take a look at the structure of what these edits look like. Okay, so this is a live edit that just happened a few seconds ago. So we get the fact that we're listening to the English channel. This page was edited. This guy added a comment when he edited it. This was a user, so not an anonymous edit. It happened in the article namespace. It was not a robot. It was not anonymous at this timestamp. Right, so this is the type of data that we're going to be looking at. Okay, so here I have my batch interval. I'll set it to 5 seconds. You can go down as low as half a second with Spark Streaming. Spark Streaming, though, is not an event-based processing system, right? So we just listen for up to 5 seconds, what our edits come in, then we apply our RDD DAG to it. So we're not like operating on every item coming in instantaneously. This is micro-batching. Okay, then I'm going to set up a checkpoint directory. This is just showing you what the edit looks like, one of the older edits last night. And here's the streaming logic. I'll let you skim through this. We're basically going to use a receiver that is going to be listening to the node.js server. Then we will convert the RDD of string JSON records into an RDD of Scala Wikipedia change object. So we are actually converting JSON to a Scala object, and then we filter out the non-article edits, like changes to somebody's Wikipedia profile page or the talk page where the discussion happens about that page. I don't care about that. I want to focus on the actual article itself, the corpus of the 5 million or so articles. And then what we're going to do is we're going to listen for about a minute. Then whatever data came in, we will write it down to a Parquet file and then do a little bit of batch analysis on what came in the past minute. So here I'm making a Wikipedia object to basically map the JSON to a Scala object. So this is what we're going to be doing. This is the same data you just saw a second ago. In here, I'm just showing you that we're going to make that into a Scala class. Okay, so here is the actual code. So we're going to define our dstream processing logic before we start capturing the live stream. So I won't cover this too in depth, but it's like quite easy to follow. We're basically here defining some stopping logic for later on when we decide to stop. But here's the start. So we check if there's a checkpoint. If there's, and this time, like we're starting for the first time ever, there's going to be no previous checkpoint. And then there's a restart function. And this is the actual code that's making a Spark streaming context. So it's saying streaming context, passing in the Spark context, and the batch interval of 5 seconds. Then we get the Spark streaming context, upon which we set a checkpoint directory, and then we print some information to mention that that happened successfully. And then here we're doing some conversion from JSON to that Wikipedia object that we want. Okay, we define that, and we make sure that the runner object is serializable. And then we're going to, with the restart function, notice that we're actually stopping and starting within restart. So restart is the best way to initialize this stream. Where is it? Right here. So restart will start it up. If it's running, it would stop it, but it's not running right now. So we can just call restart, and it should be fine. So let's start capturing some edits. Now, what we're going to do is maybe listen for like, I don't know, maybe 30 seconds to a minute. Okay, restart. Now we are sniffing for the traffic where we are getting the data. And if I run this, I can see already that we have written out, this was an empty directory before I started Spark streaming. There was nothing in this directory. But now that I'm running it, every time I run that command, I can see more files are coming in. Like right now, there's like, only 1, 2, 3, 4, 5, 6 rows. But every 5 seconds, we're appending to this Parquet file. Now there is probably even more. So if I keep running this, I'll notice that this will keep growing. Now in a 5-second batch interval, if no edits happened to the English Wikipedia article namespace, then we would filter that out. Okay, so anyway, we keep getting our data appended to these files. So it looks like we got some data, but I want to know how much data, so I'm going to run this. 95. Let's get to above 100. Oops. Yeah, okay, that's 102, so that's probably pretty good. We got 100 edits coming in. Let's go and stop Spark streaming. And now we will, basically, we're going to repartition, do a little bit of repartitioning to speed some things up. And then we will see that 13 batches were written. Edits captured were 102. So actually, one more thing I should show you is, let's get that started one more time. And I want to show you the Spark streaming UI, because it's really cool, and it got updated recently. So let me go back up here. When I do the restart, it's actually going to delete all that data in that directory. So if I print this again, okay, so I guess some stuff came back in. But now that it's running, let me show you something. There'll be a new tab now called Streaming. And we can look at statistics. It's been running, we're running batches of 5 seconds for 2 minutes. It completed 24 batches, got 322 records so far. This is the input rate. We're getting about 2.6. Let me refresh this because it's been you get even fresher, more fresh data. So we're getting more and more data, basically. The input rate is growing up. This is very small movement, though. We're getting about 2 events per second. The processing time is staying well under 5 seconds. So because of this, the scheduling delay is 0, meaning when a batch is ready, I'm not having to wait to process it. I'm processing the batch right away because my processing time is less than the batch interval, which is about 2 seconds processing time. Okay, these are the batches that have been processed, and I can see how many edits came into each batch. Okay, what if I refresh this one more time? Oh, by the way, this is showing an active job. This is the receiver thread running. It's a long-running receiver thread, so you'll notice that there's just one task, and it's not complete. It's just going to stay running until you stop Spark streaming. Okay, and I guess let me check how much came in now. $286. Let's go ahead and stop it. We will do this repartitioning for some speed improvements. Wrote 40 batches, so that means we were running for 40 times 5, that many seconds, which is 200 seconds, is how long we were running for. Approximately how many edits occur to the English Wikipedia every 5 seconds during the collection time we just had? So how many edits occur to the English Wikipedia every 5 seconds? This is the batches we were collecting. Each batch, you can see how many edits came in to English Wikipedia. Empty partitions. This is just saying that if an RDD didn't, basically it's saying that the RDD, the way it's being created every 5 seconds is that every 200 milliseconds we make a new partition. Therefore, 5 seconds divided by 200 milliseconds is 25. So we're writing down an RDD with 25 partitions every 5 seconds. Now, in a 200 millisecond window, if we didn't get any data, then that's still an extra partition we are creating. So to get around this problem, what we're going to do is actually repartition down to 4. So instead of like writing every 5 seconds an RDD with 25 partitions, we're saying, no, that's like a little bit too much. We don't have that much data coming in. Let's just repartition down to 4 partitions, and then we're going to write that down. And now I'm just basically, I read a data frame, I believe. Yeah, we had a data frame here earlier to read that Parquet data. We repartitioned it, we cached it, so that we can then do some analysis at memory speeds. How many anonymous versus authenticated user edits are occurring? Anonymous versus authenticated users. So anonymous, true, anonymous, false. So there's more logged in users who are editing it in that like 2 or 3 minute window. Yeah, let's see. We can also visualize this using Google Charts, so this is kind of cool. I'm going to visualize the same thing using Google Charts with like this speedometer thing. So I got more logged in people editing English Wikipedia than anonymous. And another goal we have is we're kind of hacking around with this lab to be able to make this dynamically change. Google Charts does support it. We just are figuring out how to do that in the training department right now. If we had a few more days, we would have figured it out. But that could be another cool challenge for you to see if you can make this move live every 5 seconds, or make your window even smaller every 1 second, see if you can make it move. How many anonymous versus authenticated versus robotic edits or bot edits occur to the English Wikipedia in the collection time? So anonymous IPs, IP addresses, logged in usernames, bots. Not much bot activity right now. 5 edits were from robots. Logged in people, 193. Anonymous, 88. Anonymous edits. Let's do some analysis of just the anonymous editors. To make our job a little easier, we'll create another data frame just for the anonymous users. On this. So basically, these are all the anonymous edits. So this guy, in just that 2 minutes or 3 minutes of collection, he actually did 3 edits. So he was like kind of active during those 2 or 3 minutes. So was this guy. This guy did 2. But can we take a stab at de-anonymizing them a little bit? That is what we did here. So we want to take those IP addresses, geo-encode them, and then visualize that on a globe map. On a global map to see kind of like where in the world are people editing anonymously English Wikipedia from. The motivation here is that most vandalism and damage to Wikipedia probably happens by anonymous editors. And I guess I'm curious, who is perhaps, which countries are doing the edits anonymously? This is not to say that all anonymous edits are always malicious, but perhaps more malicious things happen with anonymous edits than logged in edits. Okay, so I have this table that shows from a starting IP to ending IP basically which country the edit is coming from. And I'll leave it to you to kind of go through this more slowly when you have some more time. But I just want to get to the visualization, and you can see that kind of what we're doing is like joining that geocode table. We're actually broadcasting that out to the executor. And then we are then, I don't need to run the explain, then we're going to visualize it. So this is the broadcast of the smaller table, and then we're going to try to visualize almost there and do a display. Let's see if it works. The join is a little bit costly. I think it takes like 2 minutes. The table that we have of, IP range from here to here means it was in this country. It's like a pretty big table. So it's taking a bit to process. We're stuck here on this cell, but it is moving. So in Databricks, you can do this. That's pretty cool. And it's unlike any other notebook product where we can really quickly figure out what's going on. Do I need to do some more deeper troubleshooting, or is everything looking healthy? Or here, everything does look pretty healthy because it is progressing. Okay, so I don't even have to leave the page to do that. And then let's go all the way down, see if we will get a global visualization of the anonymous edits that happened in that 2-minute collection window. Okay, so let's see where it's. I'll just wait down here. I'm sure it'll be, one of those upper cells will probably complete very soon. Here we go. Do we have a global visualization? Yeah, we do. They almost all came from the US. Interesting. What time is it over there? Because Denver is a central location. Isn't it the middle of the night there? No, it's morning. So my guess is if we had done this like in the morning today, probably the edits might have been happening at different places instead of America. Okay, so that essentially. Okay, let's go ahead and continue. So I have like four or five more slides, and I just wanted to give you some maybe ideas about where you can go with the knowledge that you've gained today. So the first thing is I recommend getting some domain knowledge on Wikipedia before you continue to hack Wikipedia's data sets. To make this class, I read a really good book on Wikipedia called The Wikipedia Revolution by a really good author. I did a lot of research on what other data scientists did with Wikipedia to get a sense of what's out there. And based on that, I was able to very quickly figure out what were the interesting insights that I could derive. So without having good domain knowledge of your subject, you can make mistakes on how you interpret it, or you might not know where to go inside the data to pull out those insights. So that's one thing. I recommend getting some domain knowledge. I wanted to let you know that you'll have access to Wikipedia for about a month after class. So feel free to keep playing with the data sets. Notice that we only worked on English Wikipedia today, but there are some interesting different insights that can be discovered when you look at the other Wikipedias. For example, the Spanish Wikipedia has 1.2 million articles. The Polish one is 1.1 million articles, and we haven't even tackled those data sets yet. And then some interesting information, the top 5 countries visiting Wikipedia. US sends about almost 25% of traffic to Wikipedia. And when they go to Wikipedia, where does the traffic go? They almost all go to the English Wikipedia, 60% anyway. 9 or 10% Japan. So Wikipedia is very, very popular for Japanese-speaking people. Revision history. So the 10 terabyte edit corpus, I think, has a lot of interesting insights that I haven't gotten to really analyze yet. I've just started that work. But this is a revision history page for Apache Spark. I showed you this earlier. And it looks a little bit complicated, but it's actually really easy to figure out what it's doing. And if you figure out what this page is doing, then looking at the 10 terabytes of edits will make sense. I wanted to mention that there's this thing called edit war. This means that if there's 3 reverts in a 24-hour period, then there's an edit war going on. What this means is that like somebody comes and does an edit to like maybe one of the articles that's kind of like contested, heavily contested, like maybe the Barack Obama article, or other political things or things of that nature, right? And then if somebody edits it and somebody comes back and reverts that edit, and then maybe somebody else comes back and does an edit and somebody else reverts it. If that happens 3 times, it's an edit war, and basically Wikipedia will, some admin of Wikipedia will come and put that page in a special protected status for some period of time. I think there's like maybe 200 articles are in a permanent protected status as well. So I thought it would be kind of interesting to derive which articles ever went into a protected status and then see what was special about that article. This is showing anonymous versus logged in user edits. And we can see that in blue, usually people log in. What people seem to do is they initially edit it anonymously for a while, then they want to have a reputation, so then they become logged in users. That seems to be the general pattern. This is showing something pretty interesting. Now, this is looking at unique visitors. This is not page views, which is what we were looking at this morning. This is something different. This is unique visitors from, I think this was, the source is ComScore. So we're looking at desktop in blue. Desktop unique visitors is going down, but if you remember from this morning, there's more individual requests from desktop users, because remember we were seeing twice as many requests. This is looking at unique visitors, and mobile is going up. Now, this poses an existentialist threat to Wikipedia, because it's made on the foundation that it should be very easy for anyone to edit it. But when you browse Wikipedia through a mobile phone, it's not that easy to edit. You have to actually click a button and then scroll down through all that garbled-looking text with the double brackets and try to find what you have to edit. So the number of edits to Wikipedia is it's stagnating. And one of the reasons behind this is the rise of smartphones. So I'm not sure what the solution to this is, but perhaps the Wikimedia Foundation is working on a new HTML5 application designs to make it perhaps easier to edit Wikipedia. Perhaps while you're looking at the page on an iPhone or Android phone, you can just like triple touch a word perhaps to edit it. That would get around this problem. But overall, the number of edits in Wikipedia has been falling for the past few years. And one of the things I was hoping I could do is raise some awareness around this issue, because I do think that this is like a website worth saving. I also wanted to thank the Wikimedia Foundation. I was at a Wikipedia conference in Washington, D.C. a couple of weeks ago, where I met with a lot of people in the community to understand things that they need help with, things like coordinated attacks happening to its integrity by PR firms. And they gave me a lot of ideas that I seeded into this course. And the data scientists at the Wikimedia Foundation, specifically these three people, were very responsive when I had questions about the data and how it was collected to make sure I was analyzing it correctly. So they had a lot of domain knowledge they brought to this course. That is it. With that, I'm going to open it up for questions and answers. And it's just about 5 o'clock, a couple of minutes past. So I'm going to hang around here for 15 minutes. You're welcome to take off, or if you want to hang around for 15 minutes, you're welcome to as well. But I do have a hard stop at 15.